How we found Earth's location in the Milky Way. The boundless expanse of the cosmos has captivated human curiosity for centuries, aspiring astronomers to unravel the mysteries of our place in the universe. In this exploration, we embark on a historical odyssey to trace the evolution of our understanding of Earth's location in the Milky Way. From the early stargazers relying on primitive tools to revolutionary telescopic observations, each milestone has contributed to our cosmic perspective. Join us as we delve into the celestial revelations that have shaped our comprehension of the vast galactic tapestry, guiding us to pinpoint Earth's unique coordinates in the Milky Way. In the annals of astronomical history, the earliest pioneers embarked on a quest to unravel the celestial tapestry, endeavoring to map the stars and decipher the cosmos. Millennia ago, ancient astronomers observed the night sky with the naked eye, crafting rudimentary tools like astrolabes and quadrant instruments to chart the positions of the stars. Amid these early endeavors, the prevailing cosmological model was Ptolemy's geocentric universe, which placed Earth at the center. It wasn't until the revolutionary insights of visionaries like Nicholas Copernicus that a heliocentric model gained prominence, challenging the notion of Earth as the cosmic nucleus. Copernicus in the 16th century postulated a solar system where Earth and other planets orbited the Sun. Although his heliocentric model faced initial skepticism, it laid the groundwork for a profound paradigm shift. The subsequent development of telescopic technology by Galileo Galilei in the early 17th century was pivotal. Galileo's observations shattered the geocentric dogma, revealing a dynamic universe where celestial bodies, including moons around Jupiter and the phases of Venus, defy traditional cosmological frameworks. The transition to a sun-centered model gained further momentum with Johannes Kepler's laws of planetary motion. Kepler's groundbreaking work in the early 17th century elucidated the elliptical nature of planetary orbits, providing a more accurate description of the solar system's mechanics. This shift in perspective marked a critical juncture in the ongoing quest to understand Earth's place in the cosmos. By the late 17th century, Isaac Newton's laws of motions and the law of universal gravitation provided a comprehensive framework for celestial mechanics. Newton's work explained the gravitational forces that govern planetary orbits, reinforcing the heliocentric model and solidifying our understanding of Earth's relationship with the Sun. These early pioneers, armed with curiosity and nascent technology, laid the foundation for the astronomical revolutions that would follow. Their endeavors set the stage for the unfolding cosmic drama, propelling humanity toward a deeper comprehension of our place in the vast celestial expanse. In the early 17th century, a tool emerged that would revolutionize humanity's understanding of the cosmos: Galileo Galilei's telescope. Crafted with precision and innovation, this instrument became the window through which Galileo peered into the night sky, forever altering our perception of the universe. Galileo's telescope, constructed in 1609, was a marvel of early modern engineering. With a series of lenses arranged in a tube, the telescope allowed Galileo to magnify distant objects, unlocking a celestial realm previously hidden to the unaided eye. Among his groundbreaking observations were the four largest moons of Jupiter, now known as the Galilean moons: Io, Europa, Ganymede, and Callisto. This revelation challenged the prevailing geocentric model, suggesting that not all celestial bodies orbit Earth. Equally revolutionary was Galileo's observation of the phases of Venus, a phenomenon inexplicable under the geocentric paradigm. The varying illumination of Venus, resembling the lunar phases, provided compelling evidence for the heliocentric model proposed by Nicholas Copernicus. Galileo's findings sparked both excitement and controversy, as they directly contradicted the established cosmological beliefs of the time. Galileo's telescope also revealed the mountains and craters on the moon, dispelling the ancient notion that celestial bodies were perfectly smooth and unblemished. These detailed lunar observations further challenged the traditional view of the heavens as immutable and paved the way for a more dynamic understanding of the cosmos. The impact of Galileo's telescope extended beyond our solar system. His scrutiny of the Milky Way revealed a multitude of previously unseen stars, challenging the perception of the cosmos as a limited fixed sphere. These discoveries collectively ushered in a new era of observational astronomy, where evidence from the telescope trumped centuries-old dogma. Galileo's telescope not only expanded our knowledge of the cosmos, but also ignited a scientific revolution. Its lenses focused humanity's gaze beyond Earth, challenging us to question and explore the vast unknown. In the wake of Galileo's observations, the telescope became an indispensable tool for astronomers, propelling us toward a more profound understanding of our place in the grand cosmic narrative. In the early 17th century, Johannes Kepler, a German mathematician and astronomer, played a pivotal role in reshaping our understanding of the solar system through his formulation of Kepler's laws of planetary motion. These laws, derived from meticulous observations and mathematical analyses, represented a transformative leap toward a more accurate depiction of celestial mechanics. Kepler's first law, the law of ellipses, shattered the traditional notion of circular orbits. He proposed that planets move around the Sun in elliptical paths, with the Sun situated at one of the two foci. This departure from the circular orbits postulated by earlier models, such as those of Ptolemy and Copernicus, marked a crucial paradigm shift. The elliptical orbits provided a more precise description of the planet's movements, aligning with the empirical data collected by astronomers. The second law, the law of equal areas, addressed the varying speeds of planets in their orbits. Kepler observed that a planet sweeps out equal areas in equal intervals of time, implying that a planet moves faster when it is closer to the Sun, or the perihelion, and slower when it is farther away, or the aphelion. This groundbreaking insight into the dynamic nature of planetary motion further contributed to the refinement of the heliocentric model. Kepler's third law, the harmonic law, established a mathematical relationship between a planet's orbital period and its average distance from the Sun. Specifically, the square of a planet's orbital period is proportional to the cube of its semi-major axis. This law not only provided a universal principle governing the motion of all planets, but also underscored the inherent order and harmony in the cosmos. Kepler's laws, published in the early 17th century, laid the groundwork for a sun-centered model of the solar system. They provided a comprehensive and mathematically rigorous framework that explained planetary motion in a way that the earlier geocentric and heliocentric models had not achieved. Kepler's insights, coupled with later developments in celestial mechanics, propelled humanity toward a more accurate and profound understanding of Earth's place in the cosmic dance orchestrated by the Sun. In the late 17th century, Sir Isaac Newton's monumental work in physics and mathematics brought about a revolutionary paradigm shift in our understanding of celestial mechanics through the formulation of his laws of motion and the law of universal gravitation. This unifying framework not only explained the dynamics of objects on Earth, but extended its reach to the farthest reaches of the cosmos, establishing a coherent foundation for the heliocentric model and forever altering our perception of Earth's place in the universe. Newton's laws of motion, presented in his Philosophiae Naturalis Principia Mathematica, provided a comprehensive set of principles governing the motion of objects. The first law, often referred to as the law of inertia, posited that an object at rest stays at rest and an object in motion continues in motion with a constant velocity unless acted upon by an external force. The second law introduced the concept of force as the product of mass and acceleration, establishing a quantitative link between the motion of an object and the forces acting upon it. These laws, designed for objects on Earth, laid the groundwork for understanding the motion and the broader context of the cosmos. Newton's law of universal gravitation was equally revolutionary. It asserted that every particle of matter in the universe attracts every other particle with a force directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. This law not only explained the familiar force of gravity on Earth, but extended its reach to the celestial bodies of the solar system and beyond, and provided a unifying explanation for the elliptical orbits of planets described by Kepler, demonstrating that the force responsible for an apple falling to the ground was the same force governing the motion of the planets in their orbits around the Sun. The synthesis of Newton's laws of motion and the law of universal gravitation ushered in a new era of celestial mechanics, unifying the principles governing both terrestrial and celestial bodies. Newton's gravitational theory not only offered a compelling explanation for observed celestial phenomena, but also provided a mathematical framework that allowed astronomers to predict the motions of planets and other celestial bodies with unprecedented accuracy. This monumental achievement marked a critical juncture in our understanding of the cosmos, establishing Newton as a towering figure in the history of science and paving the way for further exploration of Earth's place in the universe. Please like, share, and subscribe for more fascinating insights and join us in continuing this exploration of the cosmos. Leave your thoughts in the comments, and together, let's reach for the stars.